We've talked about the concept of resistance in a couple of the previous lessons in this module, but resistance is one of the most important things to consider in electrical circuits, on par with current and voltage. Resistance is caused due to the nature of how electricity, or specifically how electrons, flow through a material. So to remind you of what we've done previously, we've had this idea that the structure of a metal is a lattice of positive metal ions and a sea of delocalized electrons that we've said are free to flow through the circuit. Okay, and we said that the idea that crucially that the electrons wouldn't just travel through really nicely, there would be a whole series of electron-ion collisions inside the metal. And that is the key to understanding resistance. Resistance is caused by these electron-ion collisions. So we want to think about how we define resistance, how we measure it, and factors that affect it. So first of all, the equation for resistance that we have is voltage or potential difference divided by current. So in symbols, that's capital R, it's voltage divided by current. And we measure resistance in ohms, the symbol of which is omega, which is a Greek letter. We measure voltage or potential difference in volts, and we measure current in amperes. Now this equation comes from a particular experiment which you will do where you measure the potential difference across a wire. So you have a variable power supply, and that's crucial because you need to be able to increase your EMF. And you have a wire connected into the circuit, which effectively is a metallic conductor. We have an ammeter, and then we would put a voltmeter across the wire. So this bit here between these two terminals is our wire that we're interested in taking measurements about. So we plot a graph of potential difference, so obviously measured in voltage, which is what we're going to get across this voltmeter on the against current. And if you do this for a metallic conductor, you'll get this, a straight line through the origin. And what this shows is that voltage is directly proportional to current. So in terms of where the equation comes from, voltage is directly proportional to current. That means that as the voltage increases, the current will increase. And then to turn this into an equation, we have to add a constant, which in this case is resistance. And so if we rearrange that, we get our equation. Now, the gradient of this line, just to clarify, remember gradient is the change in y over the change in x. That would be current divided by voltage. So if we're doing current divided by voltage, that is 1 over resistance. So the gradient of this line isn't equal to resistance, it's 1 over resistance. So what you would have to do to work out resistance from the gradient of a current voltage graph would be to do on your calculator the reciprocal of resistance 1 over that. If you had a voltage current graph the other way round, then the gradient would be equal to the resistance. So we get this idea that potential difference of voltage is directly proportional to current, and that constant proportionality is the resistance, which we measure in ohms, and therefore is a measure of if I provide the circuit with a certain amount of energy per unit charge, a certain amount of voltage, what current will I get? What will be the rate of flow of charge? Now, other things that will affect it is if we think about this wire that we might have, and our basic understanding of how resistance is caused. If we make the wire longer, so if we increase the length, then we will increase the resistance. Resistance is directly proportional to length. And the reason for this is if we think about a journey, if I've got to travel further, it's going to require more energy. So if my wire is longer and I've got the same amount of energy, I'm going to have more resistance to overcome, and therefore my current will decrease. So a longer wire ultimately means more electron-ion collisions, therefore a bigger resistance. So resistance is directly proportional to the length of wire. Another thing I can think about with a wire, as well as its length, is I can think about its area, its thickness. And if I was to compare two wires, one thick, one thin, you can imagine that in this case, that the electrons are not as able to move as freely. So imagine if we did this as an experiment in the classroom, and I was to say to a class of 30 students that they all had to travel through a single door, compared to if I told the same class of students that you've got to travel through a double door. Now, the class of students would find it much easier to go through the double door because they have effectively more space to spread out, and they have the capacity to travel through that much quicker than if I told them to go through a single door. You can imagine the group of 30 students crowding almost around the door because of the resistance in their path. And so resistance is inversely proportional to the cross-sectional area of the wire. So effectively, in this case, which is a thick wire, resistance is much lower. In this case, with a thin wire, the resistance is much higher. So remember, inversely proportional means opposite. As one goes up, the other goes down. So resistance is inversely proportional to cross-sectional area of the wire. Another thing that we could change about the ions now is I could heat them up. So I could change the temperature. And you should remember from P1 that temperature is a measure of the amount of kinetic energy that particles have. So if I increase the kinetic energy, what's going to happen is these particles are going to vibrate more. So I increase the temperature, I increase the kinetic energy, I increase the amount of vibrations. So you can think of this a little bit like, imagine I have a goalkeeper for a penalty shootout, and I have two goalkeepers. I have one that stands in the middle of the goal and does nothing. It would be very easy for a skilled footballer to take the ball and kick it straight past the goalkeeper, no problem at all. If, in contrast, my goalkeeper is moving around, diving all over the place, there's a much greater chance he's going to save the ball. It's the same thing with positive metal ions in a metal lattice. The more that they are vibrating, the greater the chance that the electrons are going to collide with the ions because they're moving around more, they're vibrating more. So temperature is also directly proportional to resistance. So the bigger the temperature, the bigger the kinetic energy, the bigger the vibrations, and therefore the bigger the resistance. And the last thing that affects resistance is the material itself. So different materials will have different amounts of resistance, which we call resistivity. But different materials will have different degrees of resistance depending on how many electrons they have to conduct, what type of bonding they have. So we've talked pretty much exclusively about metallic bonding, but electricity can flow through materials that aren't made out of metals, but quite often it just doesn't do it as effectively because the resistance is so much greater and there isn't a sea of delocalized electrons. So it's very important that we consider the material itself in terms of its capacity to allow current to flow freely and therefore have a lower resistance or a higher resistance.